also a warm welcome from me. My name is Marius Gatzen, and I'm going to present you welding simulation in joining and assembly with our, I would say, second most important product, Simufact Welding. In this webinar, I will go through a short introduction. I will show you a few slides about what welding simulations are about and what we are focusing on with our product, Simufact Welding. I will then show you live in the software how to set up a typical welding simulation. Will only be a short example. And after that, I will show you some real examples that will picture out the different perspectives that you can use this software to solve your problems. But first of all, start with the introduction. What we are dealing here is welding. And welding comprises of several different phenomena that we need to consider in order to create a sufficient simulation approach. First of all, we have the process zone. I would call this the area, the typically very short area where the energy input takes place, whether it be a laser beam, whether it be an arc welding process or electron beam process. Typically, you have melting of material, you have strong fluid dynamic effects, melt pool fluctuations. Then we have spatter that can diminish the quality of your weld seam, and the weld seam quality after solidification itself can be determined by pores, by ripples, and when we're speaking about brazing, for instance, also the wetting behavior. Then we have the next type of effects, which are metallurgical effects. Here we have to consider things like phase transformation when we talk about steel, for instance. Also hardening is something that needs to be considered when you determine your welding, your structure and your system. And also when we are working with filler material, we also have to consider chemical composition, change of chemical compositions. This is, for instance, a very important matter when we are dealing with aluminum welding, when you use additional filler wire and want to reduce things like crack building or something like this. And then, of course, we have structural effects. Due to the very localized heat input, we have distortion due to shrinkage in cooling, and also we have residual stresses, which are very important. We have gaps that can open due to distortion while we are welding, and also we have to consider the impact of clamping devices. So an engineer that has to set up a welding process, he also has to think about these three phenomena. So in the last 30 years, when computers got more interesting to picture out possible ways to simulate all these process and these phenomena, people came up with the idea that you have to separate all these phenomena into three different simulation types, which are pretty much the same that I just showed you. The first one is a process simulation. A process simulation is something that takes care of the very narrow area where you have the heat input, where you have your melt pool, where you have an efficiency that needs to be simulated. For instance, when you have laser welding, you can have things like a keyhole that is building, you have multiple reflections inside the keyhole. All these things need to be considered in a simulation. Usually, these kind of simulations are processed with CFD, or fluid dynamic simulations. There are only a very few commercially available solutions for this, and it is often very hard to simulate these kind of effects in an entire simulation. Then we have, of course, the material simulation, where you take care of the material properties, phase transformation, hardness, chemical composition. And then, of course, there is structural simulation, and all these three types of simulations needed to be linked together. So, as I already pointed out, the process simulation is usually something that you would approach with a CFD code. The structural and material simulation is something that can be done with FEM codes or with a structural simulation. The idea how we can link all these three parts together is that we use something that is called an equivalent heat source. An equivalent heat source is a three-dimensional energy input, a representation of the process simulation itself. This is something that needs to be calibrated, of course. Usually the very easy one is to do a quick thermal simulation and then compare the energy or the shape of the melt pool that you get here with something like a micrograph cross-section. And what you then get from this is a calibrated three-dimensional heat source. And then you can swap your process simulation with a simple thermal simulation that gives you the transient temperature field. So a thermal simulation is also very easy to connect to the other three types of simulation. They all can be accomplished within an FEM code. And then, for instance, when you use the equivalent heat sources, you get a time temperature cycle from the transient temperature field that determines, or that can be used as the input for the material simulation, where we then can calculate phase transformation, the phase properties, and things like hardness. You also get the weld pool geometry and the geometry of the heat effective zone, which is important to simulate deformations, hardening, and residual stresses in the mechanical simulations. The material simulation itself also gives information about the properties of the material and, of course, also things like transformation strains, which are used as input for a mechanical simulation as well. And since the whole structure can change its shape, for instance, contact properties can change, there are gaps that can open during a welding process. This also has a connection to the thermal simulation, and the same stays true for the material simulation, which can change also things like thermal conductivity and so on. So what we have in the end is a coupled thermomechanical welding simulation, and this is what our product Simufact Welding provides. So Simufact Welding is not a product where you can sophisticatedly simulate a process zone. You have to rely on these equivalent heat sources in order to get a fully coupled thermomechanical welding simulation, which is also often called structural welding simulation. So this is an overview about the modules that we provide with our software Simufact Welding. It is usually pictured in this kind of hub structure. In the middle we have the welding hub, which gives you the very basic capabilities within a GUI, where you can set up a welding simulation. You can control certain things like the equivalent heat source, the weld lines, the succession of weld lines. You can align your different parts. You can take care of boundary conditions like clampings, bearings, or other sort of fixtures. And we also provide different modules that would alter a little bit the default settings, whether you want to simulate a laser beam welding process, an electron beam welding process, an arc welding process, or a brazing process. We also have the possibility to perform a stress relief heat treatment, which is basically putting your welded material or even your unwelded material in an oven and subject it to a certain kind of temperature curve. And we also have an additional module that takes care of resistance spot welding, which is a little bit different from the other modes because it allows you to really simulate the movement of weld guns, and is also taking care of electrical effects inside the material. So what is the usual workflow in our software? All starts, of course, with CAD geometry. A CAD geometry usually has to be FE meshed in order to be able to use in our software. We then input the FEM mesh into Simufact Welding GUI. We then add boundary conditions, for instance, like clamps or fixtures. We then add also the heat source, and we also take care of a certain material model. Simufact Welding comes with a default set of materials. We have a library of about 30 materials that are already available, and the user is also allowed to define its own material. So this all is called the pre-processing, which can be accomplished in our GUI. From the GUI, once you have done the pre-processing, a solver input file is written and it is delivered to the solver. And the solver, you don't have to look at the solver, it will all run in the background. And once your first result, let's say you have a transient simulation and you want to look at the result every 0.5 seconds or so, then as soon as we have the first result, you can look up the result in our GUI once the first increment has been calculated. And this is then, of course, called post-processing. What can I learn about welding simulation with our software? Well, of course, the first thing that you can test is different welding sequences. If you have, for instance, a quite complex structure that comprises of several different components and has a lot of weld seams, you can test manually different weld sequences and look if they will improve the distortion behavior, the stress behavior, or the behavior within a clamping system, which is also something that you can test. You can change, of course, the clamping conditions. You can even load in, or you can use CAD data from a clamping system. So it's not something that you may rely on our internal methodologies to set up clamping conditions. You can really use real clamping CAD data. You can use different heat sources. For instance, you can also use heat sources to perform something like preheating and look if for instance, the gap closing or opening will be better, or if stress is distributed more properly. You can also change the material, of course, and look if certain material will work better. You can work with cooling times, something that is very important to my experience when it comes to distortion reduction. And you can also choose whether it is better to use one seam or even use multi-layer simulation or something like this. Okay, so this is simply a short overview about what Simufact Welding is all about. So we are talking about structural welding simulation, which starts or which reduces the real welding process itself, so the interaction between heat source and material, to an equivalent heat source. And to show you how this is all look, how this looks like, I will go into our software itself and show you how you usually can set up a welding simulation. So this is the GUI of Simufact Welding. It comprises of a process tree where you can organize your different welding simulations. It has an object catalog where you can manage and organize all materials like the geometries, your materials itself, the weld lines, and the different heat sources, and then drag and drop them to the different processes where you want to set up your welding simulation. And also we have an overview, a window where you can see the model and the results. So when we want to set up a new welding process, we can simply do this from the context menu, start a new process, and then you see we can choose from different types. For instance, arc welding, laser beam welding, electron beam welding, brazing. Then we have the specialty, which is resistance spot welding. We have the stress relief heat treatment module, which is simply an oven. And we also have this special thing, which is called cooling and clamping, which could be a simulation, an intermediate simulation between two welding sessions, where you have to change certain clamping conditions, or even you want to unclamp your already welded structure. And in this condition, you don't have to set up weld lines and something like this. So I'm going to choose arc welding here. Then you can predefine how many components you want to add into the simulation. Let's say in this case 3. You can choose between different boundary conditions. We have several different boundary types. One, for instance, is this bearing type. Bearing is simply a table, so everything can slide on it, everything can separate from it, but nothing can go through it, so to say. Then we have 2 types of fixtures, fixed geometries or fixed nodes, which are very hard numerical boundary conditions. And we have a so-called clamping boundary condition, where we can really define boundary conditions that will also apply a load or a force to a surface. So for this example, I'm going to choose, let's say, 4 fixed geometries, 1 bearing, and I also want to have 1 robot. The robot is the object that organizes the welding process, meaning all the weld lines, all the heat sources, and also takes care of filler material. So I'm going to need at least 1. What you then have here is a predefined simulation. So this is all variable. If you just see that you have missed one of the components, you can add, for instance, a new component. It's not a problem. And then you have 4 components. You can also delete certain material and add it later. This is not a problem. So you have the whole flexibility here. So, and then you see we have component containers. We have containers for the bearing. We have containers for the fixed geometries, and we also have a container for robot. And this one needs to be filled up with things from the object catalog. And the first thing you usually start with is the geometries. In Simufact Welding, we need to import meshes. This is for historical reasons. In the near future, we will also provide a solution where you can also import CAD data and then mesh them inside our GUI. So we will start with a mesh. For instance, you want to have this kind of sheet, and as soon as I drag and drop this on the component container, you see it also pop up here in the model view. So this is simply a flat sheet, and I'm going to add 2 more to them, and you see that these 3 sheets are organized in 3 different containers, so they can handle differently. For instance, you can attach different materials to them. You can also move them to each other. We have all possibilities in the GUI, for instance, to move these things around and alter them. And it is quite comfortable that you can move them in every direction. The original geometry in a container will always stay the same. So if you want to use the original geometry for another process, it will always be the same when you have it here in the container. So we also can, of course, rotate material components, and we also have a very nice feature which is called positioning. It is not gravity positioning. We will add also gravity positioning in the future, but for instance, you have the possibility there is something flying around, but you want to attach it to the surface. Just click here, and then it will be attached automatically to the surface. Okay, you see that these containers are still red, and in order to make them applicable for the simulation, we need to add additional information. After we have set the geometries itself, of course, we need the information about material. And when we look into this material, which is from our database, this is basically a material that comes from our database. It's a general steel, and it contains all the information about the thermal properties, the mechanical properties, and especially about flow curves, which is one of the most important parameters that you need for your simulation. When we look up this material, you can see it here. For instance, we have all temperature-dependent material properties, specific heat capacity, mechanical properties like Young's module, thermal expansion coefficient, and of course a whole set of flow curves. Most of our materials also have electric properties because these materials are also used for resistance spot welding. And some also have creep properties, but there are only a very few at the moment, but we will increase the number. Okay, so this is a general steel that I simply have to drag and drop to the material. I will put in the same material for all 3 sheets. And then the components themselves are ready for simulation. Of course, we also need boundary conditions, because without boundary conditions, the simulation cannot start. So at least we would need something like a table or so. And luckily, we have already predefined here a container for bearing. What we can do in Simufact Welding is generate a geometry for boundary conditions. If you don't have, let's say, CAD data for your table, for your clamping system, or for what else. And you can, for instance, create this kind of boundary condition, which is only a surface meshed volume. And yeah, you see it is pretty easy to generate this kind of stuff. But in this case, I will use a predefined, which is this bearing. It looks pretty similar, but it was predefined. And you see you can also drag and drop material from the container. I will then add some additional fixtures for the webs here, for these beams. And you can simply drag and drop them. So you're also allowed pretty easily to move these kind of boundary conditions around if you want. For instance, to test several different clamping conditions. So then all boundary conditions and components are set. Then we come to the most interesting part, which is the robot itself. In Simufact Welding, we need to create weld lines, and we can do this pretty easily on the model itself. So, for instance, we want to have a trajectory first. We need a weld line that is defined by points that we will pick by ourselves. For instance, you want to have a weld line around here. And then you can simply drag and drop this trajectory to the robot. And you see there is already a representation of the weld line with a certain alignment, which is pictured here by these red arrows. We can later change also this direction to a more meaningful type. We also can add material to the robot, or let's say we have to add material to the robot. So if we want to use filler material, this material that we attach here is the material of the filler itself. And of course, we would need a heat source. A heat source for this example looks like this. It is a simple three-dimensional Goldberg heat source where I can define a length, a front length, a rear length, width, and the depth. And I can also define a welding speed, and I can define the net energy per length. We have different possibilities to define the net heat input. You can whether use indirect power, where you set in something like current and voltage, which would represent the mean value of your arc source. But you can also use direct power, which is a power value, which is more usual, for instance, for laser or for electron beam welding. You can also up ramp or down ramp them. Okay, so in this case, I will use a predefined heat source. I attach them here, and you see there's already a representation of the heat source here. We can see it a little bit better when we change the alignment of the weld line. Okay, then let's go into the robot itself. It comprises of 3 menu types. The first one is the times. Here you have an overview about the number of trajectories. In this case, it's only 1. Maybe I will add a second one just to picture you what you can see. So I have added this one as well. And, oh, sorry, let me first place this. And then you see there are 2 trajectories. You can also change the direction, change the succession. So for instance, if you have not 2 or like 80 or 100 weld lines, you can easily change the succession by just drag and drop them here in the times menu. And then we have, of course, the trajectory type, and here you have the possibility to align your trajectory. So you see the arrow here. You could say the arrow would point in the direction of the arc or in the direction of the laser beam, and of course you don't want to weld from this side. You want to weld in a 45 degree angle, and this is what you can set up here. So we have an automatic recognition system that would, for instance, use the look for the component center of these 2 components automatically. In this case, it will align the weld line in a 45 degree angle. If this is not what you want, you can simply change also the degree based on this. And you can also change, for instance, you can have an offset or something like this. When you now see here, you also see a little bit better the representation of the heat source. But we will go with this one. So you have 45 degrees here. And then we go to the next setting, which is the fillet generator. Fillet generator is something that we have put in the software in order to have a very easy to use tool to set up filler material. Usually when you use CAD data for your simulations, you don't have CAD representations of the weld lines. When you have them, then it is also okay. You can simply mesh them and then drag and drop them from the object catalog to your trajectories. But in most of the cases, you don't have filler material. So we have this fillet generator, which uses templates, two-dimensional templates that looks like this, and they are very flexible. So, for instance, when we want to have an A value of 2, you can see that there is this two-dimensional template which is swept along the trajectory line. So, and this works also very good for curved trajectories, not only for straight trajectories. And it's a very easy way to add in your filler material. You can also change, for instance, the curvature, whatever. Oh, sorry, that's a bit too much, that it looks like this, or even the other way around. And I will go with this one. And in order to make it a little bit more easier for this example, I will delete the other one. So we have in this simple example only one weld line here. And then the simulation is pretty much set up. So you have all your components, you have all your boundary conditions, and you have set up your weld lines. In order to make it a little bit more easier here, I will only perform a thermal simulation, which is usually the thing that you would need for calibrating your heat source. In order to speed up our simulations, we have a lot of possibilities in Simufact Welding to parallelize the simulation. We can either use different domains, and we can also use what is called shared memory parallelization, which means that the simulation of each domain is shared to different cores. And so this would add up. For instance, if I use 2 domains and 3 SMP, then I would use 6 cores for my simulation. In order to have a simulation run, you also need to set up a time. This time is now automatically set to 5.5 seconds because this is the length of the weld seam, but simulation is not limited to this time. So you can simply say 20 seconds, and then you also have a certain amount of cooling after the welding is done. Yeah, and then we basically have it. We can start the simulation and look what happens. So here's the thing that you need to understand. Usually welding simulations take a considerable amount of time. This is due to the sheer fact that we are dealing with phenomena that is very localized and usually on very large structures. So in order to have a good mesh, you need to have this kind of mesh that you see here, so which is typically very fine in the fusion zone, and then should be a little bit more coarse in the outer regions. This model here has a considerably average amount of elements, so we are talking about around about 50,000 elements. Simulations in welding can easily go up to 500,000 elements. So number of elements are usually very big. And what you also need to consider is that you have that you need a certain overlap of your heat source in every increment. So when you have, for instance, several meters of weld seam, which is not so unusual to our customers, things usually take a little bit of time. So this is not the typical crash simulation, I would say. So let's see. Yeah, I did a little bit of a mistake here. You see, yeah, the simulation starts. So the fillet gets heated up. You see that we use this kind of quiet element, which means that the filler is activated when it is hitting the maximum temperature, the melting temperature, and it gets mechanically activated when we go below melting temperature. In this case, I did a small mistake. What I should have done is to project the heat source to the surface of this one, which is easily be possible in our software. I can simply show you. We go to trajectory, and then we project the heat source to the surface of the fillet, of course, so that then the heat source also will lie correctly, and you see it will go then through the fillet and not through the components, and then we can restart the simulation. Okay, but I think you get the idea. Of course, like in every good cooking show, we have already a finished simulation here, a thermomechanical simulation, so not only a thermal simulation itself. And what we use here is several robots, so you're not limited to one robot. You can use, for instance, 3 or up to 100 robots at the same time. The advantage is that you can also simulate what would be possible in real life with 2 robots, that you can weld 2 weld lines at the same time. Okay, let's jump to the end. What are the typical results that you can get from the simulation? First of all, of course, you can see look at the peak temperature and see if heat has been distributed correctly or if something was too hot. And then, of course, the more interesting one is the distortion. So this is the distortion that comes from expansion and shrinkage of the material during the temperature time cycle. We have also the possibility to overscale it a little bit so that things look a little bit more dramatic. Okay, this is maybe too much, but let's look at this, for instance. And you can also compare it to the initial state. Then we have all sorts of stresses, for instance, the effective stress, which is, to my knowledge, from Mises, effective from Mises stress. We also have a lot of displacement varieties, for instance, displacement in all kind of coordinates, and also, of course, strain, for instance, plastic strain that would usually happen here in the weld line itself. And of course also yield stress. You can also picture the boundary conditions here. So for instance, in this simulation, we have fixtures here at the start, and at a certain point, these fixtures get deactivated, and after that, the simulation can, the distortion can change a little bit. All right, I need to hurry up a little bit. So I hope this will show you how the software in general works, how easy it is to set up a welding simulation. But of course, I also want to show you some examples of real problems that our customers solve with our software. So I'm going to show you 3 different examples, and I'm going to show them in the software as well. First of all, we want to start with a suspension arm. This simulation was set up from a customer from Brazil. They had a problem with this material, with this component, which is a suspension arm. It is a multi-stage simulation, which means there are several parts added after the first session of welding is done. And for instance, the first step of simulation, the first step of welding is welding this tube and this pin to this frame. And you can see here the temperature input. So we have two weld lines around here, and we have another weld lines here, and around the cap here. And then there are another one. Okay, and then what they were looking for is distortion. And after this first step, distortions look okay. The critical part here is the pin in front. So if this has too much divergence from what they want, a usual car would get very noisy. So this one looks pretty okay. But then you have a backplate that is welded here to this one. And this is stage 2. In order to do this simulation, you can simply make a copy from the previous result, add additional material, and then start all over again. So you can see this here. This is the distortion result from the previous simulation, and this is the new plate that is added to the simulation. And then they start welding with two robots around here and around here. I will speed this up a little bit because it takes a little bit of time. Let's say to this. And what happens then is the shrinkage of this long weld line and also of this as well. And things get problematic here. When we look at the initial position, you see that there is very high distortion here in front of this part where the pin is, and this is way too much for the customer. So they were looking for a solution. So we have a distortion here of about 14 millimeter, which is simply too high. And one idea to get rid of this problem was to use pre-bending. We are allowed to show this because what I'm going to show you now is not the final solution they made. But it was one of the things that they tested in order to check if it gets better or not. And to do this, we can use these already mentioned intermediate simulations, which is only a cooling and clamping simulation. So this is the state where the backplate is added to the previous frame just by a few tack welds. And what they do then is they use clamps and a fixture here, and then this thing is getting bended. Oh, sorry, this is already the final result. So this one is getting pre-bended. And they push it down to about 17 millimeter. Because the idea behind is if we then weld along this line, shrinkage due to the shrinkage of the weld seam will then increase distortion in minus that direction upward, and then we will end up with a fine distortion distribution. And this is what they got after this. So then after pre-bending, they weld again along this part. In this case, only with one robot, because in the meantime, they are also found out that using two robots is too much heat input at the same time. So they use only one robot. So I'm looking at the time. I will also increase this a little bit to show you the final result. When we now look at the distortion, you see that we here in the position of the pin where the critical area is, we have decreased the distortion from around 15 millimeters to about 5 millimeters. Okay, so to wrap this up a little bit, they had a critical deformation, then they used an imposed pre-deform before the actual welding of the second part, and then they get an improved deformation after welding. So this is an example for using multi-stage assembly simulation with our software. Then we come to another part and a completely different background. Here we have distortion. We need to look at distortion trends of a very big part that is only simulated, which is only manufactured in very small lot size of 5 or so. And so if there is a problem during welding and they need to produce waste in order to get the best clamping system and welding succession or weld line succession, then it will cost a lot of money. And I will also go over this quickly. So this is the crossbeam I'm talking about. It is it only existed on Scratch when the customer asked us to simulate this. And what they wanted to see is tendencies of distortion. So they simply wanted to know where are the critical points when we put it in a certain fixture system. And when we look at the final result of this, you see there is some critical deformation here, which would make it harder to add additional parts after this or to even put it out of the clamping system. And this was really the problem they had here. This simulation here was not a solution for them, but it was a good measure to see what kind of clamping system they need to create for this. And we first run this as a usual transient simulation. This part has very long weld seams of about 2.5 meters. And as I already pictured out, when you use this kind of structural welding simulation in a transient way, where you heat source has to move along every weld line, this can take a considerable amount of time. So this simulation really took about 80 hours. And just to look at certain tendencies, this was way too long for them. And in order to improve or increase the simulation time here, or to reduce the simulation time, we have certain simplification types in our software. The first one is the so-called single-shot method. In the single-shot method, we don't have a transient heat source anymore that goes along every weld line, but we have a predefined temperature curve that is applied simultaneously to all weld lines. Of course, this is a simplification of the reality, but in most cases, and if you only want to look at tendencies, this will work pretty well. And you see this simulation here is the so-called uses the so-called single-shot approach, and it pretty much shows the same tendencies, only with different magnitude, but it shows the critical areas, and it runs only for, let's say, 20 minutes. And then, of course, we have the most simplified approach, which is the so-called shrinkage approach. This is shown here. The shrinkage approach is the easiest one, where you only apply a certain shrinkage to the weld material itself. So the weld lines will only shrink, and then they will pull like strings at all adjacent parts. And even if we use this very simple approach, you see the tendencies are still the same. And this kind of simulation only takes 8 minutes for this big part. So this is another way to use our software. So if you're only in a very early design stage and you have to weld material or parts that you don't have very much knowledge about, and you simply want to look where problems might occur, you can also use simplified approaches. Or this was not, okay, the second one was not 80 minutes, it was 130 minutes. And the last one was really 8 minutes. And you see tendencies in all cases are the same. Of course, the magnitude is not always the same, but the trend is correct. Okay, then I come to my last example. I will only go very fast over it, which is to show you also our capabilities for resistance spot welding. So for our resistance spot welding, I have this example, which also shows you another way of dealing with our software when you really want to look at your clamping conditions. So the welding process itself was not the most interesting part here, but it was the behavior of the entire structure within the clamping system. So we have only a few spots here in the area, 5 spots that are added here. And you see we have a very localized heat input, but it also has an effect on the entire structure. Yeah, I will skip this to the end. So when we look at peak temperature, you see we have these 5 spots here. So you have 2 informations here. You have the very localized effect of spot welding. You even can look at phase transformation. For instance, this was a multi-phase simulation, so you can see the phase change here in the area from martensite, bainite, perlite, and ferrite, and so on. But what was more interesting for the customer was the behavior of the entire structure within the clamping system. And it was pretty okay, but there were some certain divergence here in this area. So they wanted to know if it is possible to get also rid of this the deformation. And the way to go was not changing the welding process itself, but to change the boundary conditions. So they got rid of some of the clampings. And what was the result of all this? Let's put this to the same scale. So the deformation here was gone. So getting rid of a few clampings got the customer to a better result. And this is also something that you can test. You're not focusing on the welding itself, but of the behavior on the behavior of the entire structure within a clamping system. So to sum this up, this was the situation before. Then they decided to get rid of some of the clamping systems, and the distortion behavior got a little bit better. So I hope I was able to show you the capabilities of our software and the different approaches and different questions you can answer with it. And yeah, thank you very much for your attention.